Looks like we're all getting set up. Welcome, everybody, to the SF Big Analytics Meetup. We are so glad that you're here. I'm Anya, and I'll be your host. I'm from Alpine Data. And I'll be introducing tonight's speaker after we hear a welcome from Hotel Tonight. And a great big thank you to Hotel Tonight for these accommodations and the refreshments. They're pretty much awesome. So, John from Hotel Tonight.
Welcome. My name's John. We're at Hotel Tonight. We're a mobile hotel booking app. We make it easy to book great hotels at discount rates today, tomorrow, or next week. We're about 4 years old. We love data. We love analytics. If you haven't seen our app or booked a hotel with us, please check it out. Plenty of our BI team, our head of analytics, our director Julia King is here, head of data engineering is here. We're happy to chat, tell you more about what we're doing. We're glad to host you here. We love this amazing space. We like having friends and new colleagues to report. So do check out our app. Enjoy the food and drinks and the great speaker. Thanks.
Thanks. Well, if you recall last month at our meetup, we heard about streaming event data with Kafka. And tonight we're going to hear about Druid, which is an exciting new platform that allows business users to query both historical data and real-time event data. So you probably know Druid is a column-oriented distributed data store, which I can tell you from personal experience is a huge opportunity for enterprise business users. So our speaker tonight led the data ingestion team at Metamarkets. Our speaker is a committer on the open source Druid project, and recently co-founded Imply, a startup that just received $2 million in seed funding to help customers and support them as they use Druid. So without further ado, I give you Gian Merlino.
Yeah, thanks everybody. Thanks to Alpine Data for organizing and Hotel Tonight for hosting. This is a really, really sweet office, which ours is cool. Yeah, so I'm Gian Merlino. I work on Druid. I also, just as Anya mentioned, recently co-founded Imply. One of my other co-founders, Vadim, is sitting over there. Hi, Vadim. As people always say in these things, we're hiring. That is true for us. We are hiring. We're hiring UI people. We're hiring Druid people. If you're interested in that kind of thing, come talk to me afterwards. Other than that, I'm going to talk about Druid. This talk was scheduled for an hour. I don't think it'll take that long. I feel like that's a little bit long for a meetup, so it'll take however long it takes, but probably shorter than that. So I'm going to start with some motivation, why Druid exists, why we made Druid. Go through a little bit of a demo because I feel like pretty pictures are the best way of explaining what we're trying to do. Talk about the architecture of Druid, how it does what it does, and then talk about how you can be part of the Druid community if you like it. So the motivation behind Druid it was started in 2011. It was started by a team of folks at a little startup called Metamarkets that I used to work at, the team used to work at. And what we were doing was we were doing analytics for online advertising. So we would get impression data, click data, all this sorts of stuff from our customers, and what we give back to them was cool analytics, like business intelligence type stuff as a SaaS. So what we were trying to do was find a way to power that SaaS. We couldn't find anything. I'll talk a little bit in a bit about what kinds of stuff we looked at, but we couldn't find anything, and so we started Druid in 2011 to power that SaaS. So it's designed from the ground up to power interactive data applications. So to this day, most people using Druid are happiest using it if they're powering some kind of interactive data application. It's designed to support multi-tenancy, so we want to support lots of concurrent users. Hundreds or thousands of concurrent users is around the target. It's also scalable. It needs to be scalable. Online advertising is a kind of interesting business in that every individual event is extremely low value. Nobody really cares about any one impression, but in the aggregate, they're very interesting. So the system has to be very scalable and very low cost. So we're dealing with trillions of events per day. The biggest cluster I'm aware of is doing 3 million events per second average. That's the original cluster at Metamarkets. We also want to have sub-second queries. We're trying to power a business intelligence application used by business users. So we don't want to have a thing where there's like a query builder and you click and then you wait 10 minutes for the query to come back. We want to have an interactive experience where you're clicking all the time. So we need sub-second queries. And finally, we want to be able to do real-time analysis. So we want to be able to analyze events as they happen, not just a day after they happen. So why do we want to do this? What kind of stuff do we want to do? We want to be able to slice and dice through our data. And the reason we want to do that is because questions lead to more questions. We're not building a static dashboard. We want to have an interactive data application. One of the big problems with static dashboards is you look at it, you see a change in one of your KPIs, and you're like, well, I wonder why that happened. Oh, well, I guess I can't find that out without doing a SQL query. It's going to take a couple minutes to finish. So what we do is we take that dashboard and we open it up and let you just interactively change it. So you want to dig into the data set using filters, aggregates, and comparisons. And the interesting thing about this, when you're building this sort of ad hoc application, is that you can't determine all the interesting queries up front. So pre-computing answers to queries is not the way to go. So here's the part where I hope that the internet works. Let's go here. Can I do full screen? Yes. This is not legible. Now it's legible. So this is an example of the kind of application we were trying to build. This is an open source one that the team's been working on. You can get it from GitHub. So let me just kind of go through a workflow. So this is a data set of Wikipedia edits. This is one of our demo data sets. There's actually an IRC channel you can sit in, and just an IRC bot will tell you all the Wikipedia edits happening. So we can see pretty time series. There's not really much like useful information here, but it's kind of cool to see time series. Everyone likes that. We can also look at, so what is this, let's look at the past 6 hours. Some problem with data ingestion over there, don't worry about it. That's one good use of time series. What's the most popular pages being edited on the English Wikipedia? Actual pages. So one thing that I learned about Wikipedia, I've been doing this demo, is that most of the edits on Wikipedia are actually happening on these like meta Wikipedia pages, where Wikipedia people are just talking to each other about Wikipedia. But we just look at actual articles. Okay, The Voice, US Season 9. I don't know what's going on there. It's probably starting or ending or something. I'm sure something cool is happening. Yeah, so there's a bunch of other cool stuff happening. One thing that is interesting here, and actually makes me kind of happy, is that usually when I do this demo, one of the very top pages at any given time is stats in the current year, and I don't see it here, so that's cool. No one's really dying in the past 6 hours. So I want to do another demo that's a little bit cooler, I think. This is a Wikipedia data set. I really like it because it satisfies your desire to learn more about yourself. So I can search for myself. And I can filter out myself, and I can see, okay, I did 33 things in the past 7 days. I added 40,000 lines. I didn't actually add all those lines. A lot of that was just me committing stuff other people wrote. I'm not that good at programming. What language I use Java. That's cool. What repositories do I use? My own stuff, Druid, implied data. That probably makes sense. We can also do cool stuff like see what are the most popular languages on GitHub. JavaScript #1, that's cool, I guess. People like making websites. Who's using those? So we can also split by organization. You say, okay, JavaScript, the biggest one there is Mozilla. Java, the biggest thing there is Apache. I wonder what Apache project that is. Spark, and then Flink, and then Kafka. Those are the biggest Apache projects being written in Java right now. So the cool thing about this is that every time I do anything, a bunch of queries are getting made, and they're all coming back pretty fast. So this table is being generated by a ton of queries. The first split does one query, and then for every result in that first split, there's another query for the second split. And then for every result in that split, there's another query for the third split. So there's a lot of queries there, and that's why when I dragged the repository over, it spun for like a second and a half before going back. It was doing like, I don't know how many queries, a couple hundred, maybe. Each of these is one query. That's kind of cool. How many of you folks have used Tableau? So this UI is kind of rip off of Tableau. That might be obvious if you're looking at it. But one cool thing that we do that Tableau doesn't do that I'm pretty happy about is that these things, which Tableau calls quick filters, and just lets you filter on stuff, ours are actually live updating and in order. So these totals here are actually filtered based on whatever filters we have applied, which is something that's actually pretty important for big data. So one of the interesting things about big data is there's these long tails in distribution. You have to make sure that you are always ordering things and always limiting things, or else you're just going to dump too much data and not be able to see it all. So that's it for the demo. Hopefully that kind of illuminated what kind of app we're trying to build. So rewind back to 2011. We're trying to figure out how to build this app. We're trying to figure out how to build an app like that. So the first thing you think of is, okay, well, maybe we can just load all the data into Hadoop and figure out what to do with it there. That seems cool. The problem with that is that it's way too slow. So Hadoop queries are not fast. Spark is a faster Hadoop. It's really famous for that. Even Spark queries it's tough to get them down to that sub-second latency. So what folks usually do to make this better is you can use Hadoop for pre-processing your data. You can use Hadoop for storing your data, but you put some query layer in front of it. So some popular query layers out there, like HBase is a pretty popular one, Cassandra is a pretty popular one. Those are both key value stores. And people use those kinds of things to back applications because queries are fast. So I want to walk through the decision process that we went through when we were deciding what technology to use and why we eventually ended up building Druid. So whenever you're trying to pick a technology to build an app on, you're trying to get these fast queries, it's really important to know what you're optimizing for. There's no technology out there that can do sub-second queries for anything you can throw at it. So you really have to pick something that's specific to the kind of problem you're trying to solve. And the problem we were trying to solve is OLAP, business intelligence. So slice and dice aggregation. We want to have filters, and we want to take our data set, we want to filter it, we want to aggregate it. So some examples of things we want to be able to do are we want to be able to aggregate things over time, broken down by various dimensions. We want to be able to know like what are the top pages by edits on Wikipedia, for example. We want to know top products in San Francisco, number of unique visitors broken down by page, these kinds of things. We have a filter, a breakdown, and aggregate. Some important things we're not trying to do, we're not trying to dump the entire data set. We're not trying to support select star. Druid does have a select star query, but if that's the only thing you're using, you probably shouldn't be using Druid. We're also not trying to examine individual events. We're not trying to pull single events out. Again, that's something you can do in Druid, but if that's all you're doing, you should probably be using something like HBase. So some possible things that we looked at. The first thing we looked at was sharded relational databases. So we're like, okay, we can just get a bunch of MySQLs or a bunch of Postgres's and go to town with them. So the general idea there was to take some form of row store, like MySQL or Postgres, a general purpose database, build a star schema. So this is a pretty classic data warehousing schema where you have a fact table of things that happen. So in the advertising world, you just have one row per impression. Then you have dimension tables resolving dimensions of those impressions. So the impression might have a thing saying that the publisher ID is like 2, and then there's another table somewhere that says publisher ID 2 is the New York Times. So you do that. You can have aggregate tables for certain queries you make often to optimize them. So you can have a table that's at like minutely granularity, a table that's at hourly granularity, and so on. And you have a query cache. So for queries that you make pretty often, you're going to cache them. So this works pretty well, but the problem is that scanning this raw data is very slow and very expensive. It's really hard to get down to sub-second queries, just because the limitations of row stores for the static scanning. You can do it, but the cost is prohibitive. So the next thing we looked at, being 2011, was NoSQL key value stores. At the time, everything on Hacker News was like, well, like NoSQL key value stores can solve any problem. So we're like, okay, we have a problem. Let's try a key value store and see what happens. It didn't work super well. So we did some research and found that there were 2 basic strategies people used. One was to pre-compute the results of queries. So the idea there is you have every possible query. you pre-compute the answer. So the key is something representing the query. So if you want to be able to do like, if you want to be able to aggregate the number of ad impressions served to males between the ages of 18 and 35 in New Jersey, you have a key that's like male 1835 New Jersey. The value is the number of impressions. The problem here is that the scaling costs of processing this data and storing this data are exponential in the number of combinations of things you want to filter on and group on. And that was a problem for us because most of our objects had 30 to 50 dimensions. And this approach broke down around 5. So the other thing people do is, what's going on? Cool music. That's a good move. The other thing people do is range scans. So the idea there is you have a primary key that's just all your dimensions, so your age, your state, your gender, and all that. And then the value is the measures for that, so the number of impressions served, the revenue, and all that. So you don't have every possible combination as a key. You just have like little buckets. So if you want to aggregate, you have the most granular buckets. You don't have like every possible level. So if you want to aggregate like all the revenue for all people 18 to 35, you have to look at all the little granular buckets that match 18 to 35. And there might be a lot of them. There might be millions. The storage costs are no longer exponential. They're just linear. And the constant factor is actually, because you're putting things in buckets, the constant factor is less than 1, which is cool. So it's going to be smaller than your raw data. But it's still too slow because you're still having to scan millions of things. And key value stores can do that, but they're not great at it. So you sort of solved the storage problem, but gained a new query speed problem. So the next thing we looked at was column stores. These are things that are actually designed to solve this problem. Column stores are cool because you can load and scan exactly what you need for a query. So they basically work with, they solve the problem of the key value range scan issue of just being slow at scanning by just being like, okay, well, you know, we don't have to pre-compute every query, we can just be really good at scanning things. And then we can scan millions and millions of things super fast, like maybe that's fine. Our processors are pretty good these days. And so these are technologies that are just really, really good at scanning tons and tons of things. So you can load and scan exactly what you need. We make those scans as fast as possible. And we also make storage as efficient as possible by having different kinds of compression for different kinds of columns. So different encodings for string columns, different kinds of compression for metric columns, like longs and doubles and whatnot. And we can also have different kinds of indexes for different columns. So there's a lot of column stores out there. At the time, in 2011, there were not really any, I don't know if there were no good open source ones or just no open source ones. I want to say there were none, but I don't want to offend anybody that was working on one then. But we didn't find any that was really suitable, so we ended up making Druid, which is an open source column store. There were a lot of proprietary ones, like I just mentioned that. There was Vertica, there was Teradata, there's all kinds of stuff. But the issue with them is that they're super expensive. And nobody has that kind of money. Well, some people do, but we didn't. So Druid is an open source column store. These are what we think its key features are. So no coincidence, it matches that list of needs on the previous slide. So low latency ingestion, fast aggregates, arbitrary slice and dice capabilities. One thing I didn't mention is it has to be highly available. We're trying to power an application on this, a SaaS application. This is not like a back office thing for analysts. This is a thing for business users that actually work at other companies as a SaaS. And so we don't want to have it be down for an hour a day for maintenance or an hour a week for maintenance. We want it to be up all the time. So everybody who wants to log in, they can see it. And we also support approximate and exact calculations. There's some things that are difficult to do exactly in a reasonable amount of time, like count distinct. So for count distinct, we have an exact option that will take forever, and we have an approximate option that will happen very quickly. So I'm going to talk a little bit about how we actually store the data, and this will probably be super familiar for any of you that are familiar with how column stores usually work, because it's a pretty standard column store. But if not, then it's, I don't know, maybe it'll be interesting. So here's some data. This looks like a Wikipedia edit data set. So there's a couple of pages being edited. There's a Justin Bieber page, a Kesha page. They're all in English Wikipedia. Catch a Page is being edited by someone in Calgary. That's probably our fearless leader, Feng Jin, he's from there. And Justin Bieber is being edited by probably me in San Francisco. And these are metrics of how many words are added, how many words are deleted. So the first thing that we do, and this is something that's, I think, really cool and kind of unique to Druid, as far as I know, is pre-aggregation rollup. So what this does is, when you index data in Druid, you configure it with a rollup time granularity, like minute, hour, whatever, and a list of dimensions that it should aggregate over. And dimensions are just simply anything you should be able to filter or group on. So these timestamps over here, they're down to the second. Here, we're truncated into the hour, so we have hourly resolution in this data source. And we're using all these string columns as dimensions. We want to be able to group and filter on language, city, country, and page. So this data set that used to be 6 rows is now 4 rows, because a couple of events have rolled up into the same row. And in real-world data sets, the compression you get from this rollup can be pretty significant. So one data set where it's not super significant is like time series metrics. Usually the rollup there is like 1 to 2 to 1. One data set where, in our experience, it is really significant is online advertising, the original data set we're dealing with, where depending on what kind of dimensions you have and what you're doing with them, the rollup is usually somewhere between 15 to 1 and up to 100 to 1. Sorry.
Quick question. Does it throw away the original data, or does it keep both?
The question was, do we throw away the original data or keep both? We throw away the original. So Druid, you can kind of think of it, and the way most people use Druid is they're generally using it to power some sort of interactive data application, and they're generally using it to load data from something like S3 or HDFS into itself, and then power queries off of that. But it's generally not used as your only data storage. So it's generally used as something where you can reload data into it if you want to change the way you're loading it.
So what kind of compaction do you use?
The question, what kind of compaction do we use? Do you mean like for updating data?
No, to make it compact.
Sorry, what do you mean by compact?
When you're saying the language, there can be only so many languages. So are you compacting the code and things like that also?
Oh yeah, so I'll talk about that in a future slide, but we're using dictionary coding for that. I'll talk about that, I think, on the next slide.
And what about the text and image?
We don't really take text and image. So we don't support images. And are you talking about full text?
Text like name.
Yeah, so it's dictionary coded. Text is always dictionary coded. Yeah.
So are you using these aggregations for like pre-computations or like online when you have to clear?
These aggregations are done at indexing time, at ingestion time. So the next thing we do after we roll up is we partition by times. All data in Druid is partitioned by time, and there's a bunch of reasons for that. But most of them just come down to there's a lot of cool optimizations we can do if we assume you're always already partitioning on time. So there's a huge list of them, but like a couple of the neatest ones are ones that we can support constant time drops of older data. So a lot of people will have a requirement where they're like, I just want to age out any data older than 6 months. We can do that in constant time without doing a big compaction in the database. We can also support appending data in real time to newer parts of the database without affecting any historical data. And there's a bunch of other stuff we do too, but those are a couple of interesting ones. Anyway, so we partition data by time. So those 6 original events roll up into 4 events are now going to be in 3 segments, 1 per hour. So the storage granularity of your segments is configurable. Most people are doing somewhere between 15-minute segments and day segments. Those are sort of the normal ranges. These are per hour. Each of these segments, once built, is immutable. So immutable stuff is really cool. You don't have to worry about concurrency. You don't have to worry about locking. You don't have to worry about thread safety. So there's immutable data. It's located on the Druid nodes and the vast majority of data in a Druid cluster, unless you're throwing it away very quickly. But most people are keeping data around for at least a few days, usually months or even years. So the vast majority of data will be in these immutable segments. No contention between read and writes. The concurrency model is that one thread scans one segment. Generally, a segment scan is going to be a couple hundred milliseconds. And this is sort of the basis of our multi-tenancy. So there's a query priority system where we have fairness and we have priorities, and we make sure that we interleave segment scans appropriately to achieve the multi-tenancy and concurrency goals. So within each segment, Druid's a column store. Things are stored column-oriented. So if you look at a segment, sort of start from byte 0, go all the way to byte whatever, the first chunk of stuff is going to be the page, then there's going to be the languages, then there's going to be the city, then there's going to be the country, and so on. So this is cool because most queries don't use most columns. A typical Druid data source has, the normal range is maybe 10 to 100 columns. And most queries are going to use a small number of columns. So like 3 columns, 4 columns, 6 columns, something like that. And so it's really good to only have to scan and load what you need. Also, the data section and index sections are separate. So if you're only filtering, you're only going to use the index, not the data, so the data won't be faulted in, and so on. So this is how we store string columns. We store string columns with dictionary encoding. So what this page columns get stored as is Justin Bieber is going to be assigned 0, and Cash is going to be assigned a 1. And so the page columns get stored as 3 zeros and 3 ones. The language column, English, is going to be 0. There's no other thing, so it'll be stored as 6 zeros. This is good because it means we can do random access to any row, so that we support fast random access of any column, any row, and it's also compact. The way we do filtering is with bitmap indexes. This is we're not the only column store that does this, but it's not universal. It's more common in search systems. But this is how we do filtering. And bitmap indexes are really good if you want to do Boolean filtering. So Druid's really, really good at doing huge numbers of ORs, lots of ands. A lot of people build UIs where are just generate on the back end like 10,000 or a 10,000 item OR clause, and that works pretty well in Druid. So the way these indexes look is, so Justin Bieber is in the first 3 rows. So there's going to be a bitmap that's just 3 ones and 3 zeros. Kesha's in the last 3 rows. There's going to be 3 zeros and 3 ones. So using these, we can resolve any Boolean predicate just by looking at the indexes. This is kind of a little bit of a silly example, but still. If we had a query that's Justin Bieber or Kesha, so we'll load the Justin Bieber index, we'll load the Kesha index, we'll OR them together, we'll get this index over here that says, okay, well, we actually do need to scan every row. And most real filters, you won't just get all ones out at the end. So there's a pretty significant time savings. So that's kind of how the, oh, sorry, what's up?
For search within a stream, will that require full scan of the index, or are there some optimizations there?
So the question is for search within a string, does that require a full scan of the index? If it's a prefix, then no, we can do a binary search because the index is in sorted order. If it's not a prefix, then yes, it's a full scan of the index.
What about joins between 2 tables?
We don't support joins between 2 tables. We support joins. We support star schema style joins of like a big distributed table and a small table, but we don't support joins of 2 big tables. So the main reason for that is because there is not really any way to do that and meet our performance goals of you should be able to tune any Druid query to be done in less than a second. So most people that are trying to build these kinds of apps do those kinds of joins at a pre-processing step, like in Hadoop. So.
Okay. So what happens when you add like a 257 item to your dictionary, and now your 1 byte becomes 2?
Oh, those are integers.
Integers.
Yeah, so those are integers. And you can't have more than 2 whatever billion rows in a segment, so that can't happen.
So is there any way to change the segment by instead of the timestamp? Is there any way to change that?
You want to like go into a segment and modify the data?
No, I mean you said like you can segment only on timestamp.
Oh, partitioning. Yeah, no, there is not. So the partitioning is always on time. I think that sometimes on the Druid dev list we talk about whether it would make sense to do that. I think it kind of does make sense at some point to support things like that. The reason it doesn't is because Druid just started out as really super optimized for time series data. And it's the kind of thing where rather than starting out as general and then making optimizations, we started out optimized and then over time get more general. So if you look at Druid, like the very first open source version, it was like super specialized, and over time we've been making things more general.
And should time be in like flat, or it could be like UTC or any other format? The time.
The time format. So the question is what the time format should be. In the segments, it's always in just millis since the epoch. The time format you can give it can be all kinds of times. So we support ISO 8601 and millis and POSIX and also any format string that JONATime supports, because we're just using JONATime to parse time. What's up?
I heard there's a secondary partitioning in Druid though.
Yeah, the question from the plant in the audience is, what's with the secondary partitioning in Druid? So yeah, so not everybody does this, but you can have a secondary partitioning in Druid. The first partitioning is always on time. You can do a secondary partitioning on any other dimension, and for a lot of data sets, that's pointless, but for a lot of data sets, it does have a purpose, and the ones where it has a purpose are when you're always or very commonly filtering on some particular dimension. And in that case, if you're, so like the good example of that is account ID. If you're running a SaaS and you have a lot of your customers' data in the same data source, you can do a primary partitioning on time and secondary on customer ID. Almost all your queries are going to filter on customer ID because you're a SaaS and you're not showing customers other customers' data. And because you're doing secondary partitioning on customer ID, you get really good data locality for a given customer. And so a given customer is probably only going to have to query maybe 2 or 3 out of the 100 segments that you have. Okay, so I want to talk a bit about the architecture of the distributed system. So that was, the previous section was about sort of how we store things. That's like a low-level storage format thing. This will be about how the distributed parts are put together. So in the early days, this is what Druid looked like. It's very simple. You loaded your data into Hadoop, and then from Hadoop you indexed it into historical nodes. There was no stream loads, there was nothing like that. These historical nodes are basically just pulling data from, or indexed data, those segments, from HDFS, memory mapping them, and then serving queries on them. Now what you could do is you could go to every historical node, make the same query in each one, and then merge the results yourself. And that kind of sucks, and that was just, you know, the first month of Druid. But anyway, even today, most Druid clusters, most nodes are going to be historical nodes, unless you're only keeping a very small amount of data. But if you're keeping months or years of data, most of your nodes will be historical nodes. They're the ones that serve those immutable segments. One of the first node types to get added to Druid was broker nodes, where you can make queries directly to the broker node, and then the broker node will farm queries out to the historical nodes. So you can send, so Druid supports queries like time series, top end, groupies. You can send a broker a group by query. It'll send subqueries to every historical node, merge the results, and give you the results back. So the broker is the node that most people will interact with when they're making Druid queries. So this is just sort of calling back to the original picture. Druid is now the thing that we're using Hadoop to pre-process and store our data. So the Druid segments are stored in HDFS. They're built using Hadoop MapReduce jobs. If we need to do any pre-processing like joins, which in on advertising we actually did, we were joining impressions and clicks to figure out which impressions were clicked on. We do that all in Hadoop. And then the data set that comes out that we want to do the slicing and dicing on gets loaded into Druid. So that solved the query problem. Druid, with that Hadoop loading architecture, gave us the ability to explore data arbitrarily and do fast queries. We could do sub-second slicing and dicing, and we could build that application that I was showing you earlier. But at this point, we still have a problem with data freshness. So batch loading is slow. A lot of our customers were complaining, well, okay, I don't want to wait 6 hours for data to get loaded. And so we're like, okay, you don't have to wait 6 hours. We'll tell the job loader to run every 2 hours. And then we'll do that, and then they're pretty happy. They're like, okay, 2 hours is great. And then one job will fail, and then it'll take, you know, someone will restart it, and then it'll be 7 hours, and it hasn't been loaded yet. And they'll be like, well, this usually takes 2 hours. Why did it take 7 hours? And after a few months of this, we were like, this is the worst. We're just getting paged all the time. We hate it. So we're just gonna make it real time. We want real time anyway for our own internal operation stuff, because we At the time, we're running all of our operational metrics through Druid, and so you want real-time for that anyway to be able to monitor things as they happen. So we're like, okay, we can do real-time loads. So the idea behind Druid's real-time loading is that we have an indexing system. We have this indexer that runs in Hadoop in the context of MapReduce job, although the code that's running there could be pulled out. And we have a serving system that can run queries on data. So why don't we just combine them together? Why don't we just take that indexing code and take that querying code and like put a little duct tape there and then have the machine that can index things and query at the same time? And that's basically what real-time nodes are. They really do share like 80% of their code with the batch stuff. The code that they don't share is this code for actually querying these two things and merging queries. So what happens in real-time nodes, events come into this in-memory buffer. This is an in-memory row buffer. It's like a tree that's sorted on the timestamp and dimensions. It's all the dimensions as the key. So the way queries happen on that is actually exactly the same way as you would do queries in a key value store if you're doing range scans. So if you were doing this kind of thing built on like HBase or Cassandra, the schema you would use there is the same schema that the in-memory buffer has. The difference is that in-memory buffer only has the most recent minute or two of data. After a minute or two, it's aged out and it's converted into these immutable Druid segments, these column-oriented things. And then the vast majority of data is just in these segments. So the real-time nodes, when they get a query, they query all the segments that they have on disk that they haven't handed off yet. They also query their in-memory buffer, they merge the results, and they send that back. Periodically, they also take those segments that they have on disk and they ship them off to HDFS, and then they're loaded by the historical nodes. And generally, that process takes, depending on your configuration, from a few minutes to a couple of hours. So what it looks like now is instead of having data coming into Hadoop and being indexed in Hadoop, we have data coming into real-time nodes, which is still producing segments for historicals, just like Hadoop was. But you have this extra arrow where the broker can query it as it's doing stuff. So real-time nodes are really just like indexing system that can also support queries. Another way of setting up Druid that's pretty popular is in a Lambda architecture, a hybrid batch real-time architecture. So the main reason this is popular is the ability to do backfills. So the real-time system is append only. Data comes in, it gets indexed, it goes into Druid. A lot of people have a requirement where they want to do backfills for whatever reason. Maybe they want to drop dimensions, maybe they want to change granularity, maybe they want to fix their data, maybe they want to restate their data that's not 100% right the first time. Maybe it's because the data generation process has errors in it. Maybe it's because the code that generates the data can have bugs in it and we deploy new code. For whatever reason, it's useful to be able to stream in your data in real time, load into historicals, but then also do a batch replacement later on. So we support that too. And the default way that the batch job works is it does an atomic replace of your data. And so you don't have to take the cluster offline to do any of that. It's a completely background process that when it's done, just switches atomically. What's up?
So when you do the stream and Hadoop code together in Lambda, so do you combine those things anytime? Or
So the question is, do we combine the stream and batch stuff when we do Lambda stuff? Yeah, we do. So the way that works is these are both being loaded into the same Druid table. So if you look at, well, let me back up a bit. If you look at the way a lot of people deploy a Lambda architecture, you sort of have two serving systems. You have some real-time data going to HBase, and you have batch data going into whatever you put batch data into. And so you have a query system that queries some of the real, queries HBase what it has, queries the batch system what it has, it merges things, and you have to manage the lifecycle of data in the real-time system and the batch system. With Druid, it actually has built-in stuff for doing that data lifecycle management. The only thing you have to do yourself is you have to set up the two data pipelines. So you have to have a real-time pipeline, you have to have a batch pipeline, but once the data is in Druid, the Druid lifecycle management stuff can take care of that for you.
but if there is a spike in the thing, like there's a spike in the, say, the page, the number of page hits and added, and I want to remove that roughage.
So the question, well, I actually don't understand the question, sorry.
So say Justin Weaver had an addition of say 50 pages today.
Yeah.
And it was out of ordinary. And that would skew out all my outputs. that would the averages would all be not the right way, or the averages would be out of whack. So if I want to make sure that any of those spikes and other things are to be taken care of, how would you do that?
So are you wanting to sort of like adjust your data after it's first ingested? Okay. So yeah, the question is about adjusting data after it's ingested. Usually the way people do that, there's a lot of people that need to do stuff like that. And usually the way it's done is you have your data in some canonical location. It's usually either Hadoop or Kafka, something like that. But let's say it's Hadoop. So you have your data in Hadoop, that's a canonical location. If you want to fix your data, you fix it there first. So you have a directory in HDFS, it's partitioned by whatever. Partitioned, if it's like a hive thing, partitioned by date, it'll DT equals what have you. So you fix the partition you need to fix, you fix the hour, you fix the day, and then you reload that into Druid.
I have a question.
Oh, what's up?
So, are the aggregates and everything calculated online or offline?
So the question is, the aggregates computed offline or online? Kind of both. So what's computed offline is in the batch job, during ingestion, we compute for every granular rolled up bucket, we compute aggregates for that bucket. So, you know, if you have 50 dimensions, then for every combination of those 50 dimensions, every super granular bucket, there'll be aggregates computed for that bucket. So that's offline in the batch job. In the real-time job, that's done online. And at the query time, if you're doing any query that's not grouping on every single dimension, if you're like, I want to just, you know, for one dimension, I want to filter on that and then just get aggregate everything, but it's going to have to do that because we're not pre-computing that kind of stuff. We're going to have to find all the buckets that match your filter and then aggregate those. And so we're going to be potentially aggregating millions or hundreds of millions of buckets. And doing that quickly is possible because of the column orientation. So most queries are going to involve resolving some kind of filter using the bitmaps, and then scanning usually millions or tens or hundreds of millions of rows or even billions of rows, and then computing aggregate based on that scan.
Okay, in that case, it's online.
And that's online. So the one thing that's offline is the computation of the rolled up buckets. Everything else is online. So
I have a question about the Lambda architecture.
Yeah.
Can I do query granularity of 1 hour on the batch data and 1 minute on the streaming data in order to actually do a roll-up, do a better roll-up in order to better utilize my storage?
Yeah, so the question is, can you have different configurations on the batch part and the streaming part, like different granularities? Yeah, you totally can. That's a pretty common use case. It's pretty common to have like a very granular roll-up in real time and then relax a bit in batch. And it's actually also somewhat common to have multiple relaxations over time. So you might relax the granularity somewhat after a day and then relax even more after a month or two. What's up?
When you're ingesting streaming data, if at a later point you need to override not the entire set but some percentage of it, do you have to reload in the batch mode the entire time bucket for that time slot, or can you reload only what needs to override?
The question is, if you're overriding data, do you have to reload the entire time slot? Yes, you do. So the atomic replacement Druid, the operation is a by interval operation. So whatever interval you're replacing, if you need to replace one data point for an hour, then you load the entire hour. If you need to add one column, you still reload all the columns. You only have to do it for a particular time slice, but for that time slice, you do have to reload everything. What's up?
Can you reload multiple segments atomically?
The question is, can you load multiple segments atomically? Sometimes. When you can do it is if you have multiple segments for the same time granularity bucket. So if you're doing hourly partitioning of segments, for example, and a given hour might not have just one. So in the example, there was only one segment per hour, but you could have like 50 per hour. All the segments for the same hour are loaded atomically, but segments for different hours are not loaded atomically. So,
does Druid support hierarchical dimensions besides time?
the question is, does Druid support hierarchical dimensions? There's no real innate concept in Druid of hierarchy of dimensions. Usually people that have a concept of hierarchy dimensions in their data will just load it into Druid flat and deal with that at the query side.
And one more question.
Sure.
So there are various aggregate operators. There can be a lot of aggregate operators, and for some of them, you can have approximate results by fitting up with accuracy. So, in general, how you mentioned earlier that like unique was your example where you mentioned that sometimes don't do exact combination. Is it configurable, or it's most of the time something you do approximate?
So the question is, the approximate calculations, is it configurable, when we do it, how we do it, that kind of stuff. Yeah, so when you do a Druid query, you tell it how to do it. You say, it's not, there's no flag that's like approximate or not approximate. There actually are higher level query APIs out there where you can just say like, I want approximate or not, and it'll translate the different Druid queries. Druid is native query API, which some people use directly and some people use through wrappers. But if you use it directly, it's actually pretty low level. So the way you structure an approximate query and the way you structure an exact query are actually pretty different. And it reflects the fact that at the actual computation layer, the way that they're done is very different. But in the higher level APIs that exist, it can be as simple as setting a flag. It's like approximate or not approximate. Okay. So
how do you tackle late arrival? Meaning I got an event now, but it came from an hour before on the architecture. Yeah,
so the question is, how do we tackle late arrival? There's two answers to that. The answer that is true now is real-time nodes drop anything that's late. So you define what late means. You say anything older than 10 minutes is late, an hour is late, whenever you give it a number. It'll drop anything older than that. And you are expected to pick it up in batch. So it's on you to make a data copy that does that. The answer that's not true now, that will be true in the next major release, is that real-time nodes will be able to insert old data into old segments, and then the batch system can do a compaction of them.
So you're going to change the mutability of the segments?
They'll still be mutable, but you'll be able to add to a set. So you'll be able to have, if you have 50 segments for an hour, you'll be able to add a 51st segment that just has more stuff, and then do a compaction later, potentially. So I turned out that slide about approximate stuff. Right, so these are the kinds of approximate things we can do. Approximate stuff is cool. You can drastically reduce the storage and time complexity needs of your computations. One thing that we do is cardinality estimation. That's sort of, I guess, if you talk to people doing approximate stuff, that's like the most popular thing people are doing. There's like hyperlog is what we use for that. Actually, some folks from Yahoo recently committed something that has another option for doing another option for a different algorithm for approximate cardinality that I forget what its name is, but I'm sure we can look it up later. We also do approximate histograms. So you can generate a histogram approximately. We do approximate quantiles. So people sometimes want to know median. Turns out that exact mean is really easy. Exact median, not easy. But approximate median you can do. We also approximate any quantile, so a 90th percentile, 95th percentile. That kind of stuff is really useful for people doing server metrics. So you want to know your 95th percentile page load latency, for example. You can also add your own proprietary modules. So the metrics and aggregation system in Druid is pluggable. So the Yahoo thing I was talking about that was recently contributed as open source was actually a proprietary thing at Yahoo for a few months before then. And this kind of stuff is designed to be possible with Druid. There's a What's up?
Which is for the approximate. So Spark has something called LinkDB, allows you to do either approximate it by confidence level, say after a certain, confidence, 95% confidence and I'm just returned, or time-based approximate, basically after 10 seconds, just give whatever you got. So in your approximate, do you have an equivalent of it?
So the question is, how does this compare to what LinkDB does? It's pretty different. So it doesn't. You don't give us an error bound. You don't give us a time bound. You basically give us an algorithm. So LinkDB is sort of based on the bounds you give it. It'll decide something to do. Druid is more like you should use this algorithm. So you say use hyperlog, or use this particular approximate algorithm, or use this approximate top-end algorithm, and it'll use the algorithm to do your query.
So would you say histogram here? Does that encompass like group by and sum for like multi-dimensional group by queries over string fields, for example? Like the language, if you were to say like, give me a bar chart that shows the number of edits on different languages. Do you do approximate results for that, or is that not covered in the
So the question is, what if I want a histogram where it's like based on language, not based on bucketing, I guess. So yeah, so the approximate histograms that we have here, so this specific algorithm is for, you want the labels and the histogram things to be buckets. So you want it to be like, this is like 0 to 5, this is 5 to 10, and so on. If you want the labels to be like a dimension value, like a page or whatever, there's actually two ways of doing that. One is the exact way. So you can do an exact, group by language, aggregate whatever query. You can also do a approximate top query. So the top end, there's a top end query type in Druid that's approximate. And that's a really popular choice for like, I just want to do my top 50 languages, and you'll get that approximately. It'll be a lot faster than group by, especially if the tail is really long, because it'll have to compute double tail. So there's a lot of query interfaces. I sort of alluded to earlier, there's Druid's native query API that's very, very low level. There's also higher level APIs. The native one is JSON over HTTP. There's a few SQL libraries out there. One of them is the best one that Video's made. There's a few others as well. There's an R API that's actually similar to the low-level API. Python one also, Ruby, Perl. There's a bunch of UIs. If you don't want to deal with making queries, you just want to like click on stuff. Pivot is the one that I demoed. There's also a Grafana plugin for those of you that are more into the time series metrics world and less into the BI world. Sure, is actually pretty good for both OLAP stuff, BI stuff, and time series metrics stuff. And there's Panoramics, which is the UI from a guy at Airbnb. That's sort of more like a query builder UI. You can sort of click, build a query, build filters, say what visualization you want, and generates it. Let's look at Druid today. So the Druid community is a growing community. I think this number is actually kind of old. I think it's over 200 now. But we have a lot of contributors. We love contributors. We're not running Druid as a project that's like we just do all the stuff and we drop the code on the side of the road. It's actually we're trying to involve a community of contributors. It's in production in a lot of different companies. Some of the big categories of people that are adopting it, online advertising, that's where it started. It's also a big set of users. Network traffic analysis is a really big one. So looking at like packet flows and stuff, a lot of people doing that. Operations, so another time series metrics use case, and activity streams, so like activity streams in mobile apps or page views, stuff like that. Generally, anything where you have things happening over time with some sort of time component. Druid's production ready. It's been around for a while. Like I said, it was started in 2011. It was open sourced in 2012. The original cluster at Metamarkets has been running for 4 years with no downtime for software updates. That's a high availability. There has been downtime for reasons other than software updates, like stuff just totally broke. That doesn't count. And it's used by hundreds of companies in production. So these are some numbers from the original Druid cluster, which to my knowledge is still the biggest one. So the real-time ingestion rate there, like I think I said this earlier, it's doing over 3 million events per second sustained. The performance that we usually see is 10,000 to 100,000 events per second per core. The reason for that difference is that 100,000 per second is what you get in benchmarks, and 10,000 is what you get in real life. I actually should update that. I just benchmarked it today, and it was 200,000. My events had 2 fields in them, which is totally real data. And the 10,000 number is more like if you have 50 or 60 fields and you did index. So that original cluster has about a half petabyte of segments, and I think that comprises 20 or 30 petabytes of raw data. So it rolls up into a half petabyte of segments. That's over 50 trillion raw events. That cluster has thousands of cores. It's running in AWS on hundreds of machines and tons of RAM. So this is a lot of data, and for that amount of data, this actually isn't that many machines. This is some graphs and numbers from the Druid Whitepaper that we published a year or 2 ago. The 9th percentile query latency in that production cluster was less than a second, so we're achieving that goal of sub-second queries 90% of the time. Could be better, but it's still pretty good. 95% of the time, less than 2 seconds, and 99% of the time, less than 10 seconds. I don't even know what this means. I'm going to skip it. So what I hope you take away from this is that when should you use Druid? You should use it if you want to power a user-facing interactive data application. That's definitely the sweet spot for the project. Most users now are doing something like that. So some kind of SaaS, some kind of internal tool, but some sort of user-facing data application where you want to explore, slice and dice your data in ad hoc ways. It's also cool if you want to do analysis on data as it's happening because of the real-time ingestion support. And you want to do arbitrary, ad hoc, slice and dice stuff. And it's cool if you need things to be highly available, if you want them to be extensible and flexible. There's a lot of modules, systems in Druid, there's ways to plug in your own functionality. And yeah, it's open source. There's the website, there's a Twitter that we tweet stuff on sometimes. There's a IRC channel that you can go talk to us. And this is me. You can feel free to email me whenever after the talk. Just remind me where I met you. I have a Twitter and I have a LinkedIn, and that's all cool, and feel free to talk to me about anything. Also, our office is like a few blocks from here, so if you want to stop by and ask for an invitation, then I'll probably invite you. Thanks, guys. Any other questions?
So, very impressive. So, the pipeline you built, and I assume you have a cluster of Druid nodes in order to achieve these subsecond queries, right? So what's the memory requirements for these nodes? So how large do you have to, how many nodes do you have?
Yeah, the question is, what are the hardware requirements for these sub-second queries and that kind of data? So in Druid, all data is memory mapped. So it doesn't have to be all memory, although if you want queries to be as fast as possible, it should be mostly in memory. Because it's column oriented, and because most people don't query all their data all the time, so there's row filters where, like, you know, if you have 6 months of data, you're not usually querying all 6 months, you're querying a few days at a time, or a month at a time, or a quarter at a time. If you have 50 columns, you're probably not querying all 50 columns at once. So that stuff all put together, what we found in practice, with a concurrent workload of, you know, a few hundred users at a time, from a bunch of different tables, was if we had 80% of the data memory, performance was really good. Like as good as 100%. So if you have, you know, 50, so I said that was, if you have like, you know, 50 terabytes of data, and you may want to have 40 terabytes of memory to put it in. That's sort of a rule of thumb that we developed for that particular data set, but it worked pretty well. Another rule of thumb we developed was that if your data was about 20% memory, performance would be not that great. It was noticeably a lot worse. The 9th percentile latencies would go from 1 second to maybe more like 5 or 6 seconds. And you could do that for older data if you want. So Druid has tiering features where you can say new data goes on this hardware, old data goes on this hardware. And you can do that if you want to balance cost and performance based on how old the data is. And we did stuff like that. That's why it has those features. Yeah, I hope that answers your question.
Yeah. The other question is, suppose I, you know, start building my cluster now. I have two choices. I have a Hadoop data already, and instead you have to load it into either a Druid or somewhere else. So the other choices is NoSQL. So to do this, you know, I probably architecture is different, but it's also we can do a SQL query very quickly, get the result back. So how do you compare to that kind of architecture? So like you have your pipeline, so Hadoop, and then you have Druid from in the query talk to Druid, right?
Yeah.
So or I have another pipeline which is a Hadoop MapSQL, and I can talk to MapSQL to a SQL queries, right? So and also in the memory, it's pretty fast too. So,
right. So I guess the question is, how do I compare Druid, like Druid loading from Hadoop to MemSQL loading from Hadoop? I don't know, because I don't know MemSQL very well, or really at all. So I guess I can't really say anything super intelligent. Yeah, all I can say is that there are SQL layers for Druid. It doesn't speak SQL itself natively, but there are SQL libraries for it. One that we make at Imply. It's actually open source. You don't have to pay us for it, although it'd be cool if you did. You don't have to. But yeah, sorry, I can't really say anything super intelligent about that.
So within the Wikipedia product you showed us, so are you doing all the calculations for all the combinations offline, and then like once you drag and drop these matrices, you're just pulling these groupings, or are you doing these like online?
So the question is the aggregations for the Wikipedia demo, were they offline or online? Those Wikipedia aggregations are 100% online. So what I was saying earlier is the only offline aggregation that we do is rolling things up. So that roll-up phase where you had 6 rows of data that became 4 rows of data, that happens offline, and that's if you have 2 rows that have the exact same set of dimensions in every single dimension, then they can combine into the same row, and we just add another thing that says count 2. So that's the one thing that happens offline. Everything else is online. And the Wikipedia data set, actually, for this demo doesn't get any roll-up because it's not a very high volume data set. There's maybe like 1 or 2 events per second, and they're all unique. So it actually is 100% online. So,
can Druid ingest data sets that don't have a time column at all?
The question is, can we do data sets that don't have a time column at all? No. But what some people do, and what does kind of make sense, if you don't need the time-oriented data management features, is just put the same time step in every row. And that does work. You don't get access to all the cool time-oriented features. So I guess the big ones are, the expiring old data, adding new data without doing compactions, and there's like a global time filter. So what'll happen is that you won't get this global time pruning, so the queries will take a little bit longer, and you will have to do a compaction to update anything because the features that allow you to update slices without doing compactions are all time-based.
So what kind of client API you provide? BBC, REST API?
So the question is, what kind of client APIs do we provide, and specifically, do we have JDBC or ODBC? We don't have JDBC or ODBC. I think it'd be cool. We don't have those. The one thing that's built into Druid is this JSON over HTTP thing where you just send JSON queries. And there's a bunch of higher level ones. If you check out our website, imply.io, we have actually a couple of query options that we provide as open source on top of Druid that you may find more pleasant to use than the native one.
So how do you compare Druid to Pinot from LinkedIn?
The question is, how do we compare Druid to Pinot from LinkedIn? They're really similar. One thing that I've been meaning to do and haven't done yet is actually sit down and load our data into Pinot and see how it behaves. Haven't done that yet, so a lot like MemSQL, it can't say anything super intelligent. But from what I've read from the documentation in their paper, the architectures are pretty similar.
Compared to Storm from Twitter?
So compared to Storm and Twitter. So Storm is, I would class it as like a stream processor. Like if streams come in, streams go out. And I would class Druid as a place that streams go to stay and stay a while and have fun. So it makes total sense. And what we actually did at Metamarkets for a long time before switching to a different stream processor was we would use Storm and Druid together. We would use Storm to pre-process data in real time and then send it to Druid, where it would be stored, and then we do queries in Druid. So you sort of had Kafka over here, and then data going into Storm, and we would do joins and impressions and clicks there as being advertising, those joins being important. We would do that, and then we'd send the data to Druid, and queries would happen to Druid.
So let's say I have like now a solution where I process data or events coming online in Storm, and then I store it in HDFS, and then I can use like Druid to pull the data, do the aggregations, and have the interface.
So I guess the question is about how would you actually get stuff from Storm to Druid. So there's a library called Tranquility that's part of the Druid project, and it has a direct adapter from Storm to Druid. So we actually have a bolt that's a Druid bolt for Storm. So at the end of your Storm topology, you can just have a Druid bolt, and you configure it with your cluster URL, and then just push it into your cluster. We also have one of those for Samza, and we should have one for Spark streaming pretty soon.
How does it compare to Presto, or are they different? What do you think?
So the question is, how does Druid compare to Presto? I think they are somewhat different. So I think of Presto as something that pulls data from somewhere else and does queries within itself. So it's you have data in Cassandra, you have data in HDFS, Presto will pull data out of where it is, Hive, Cassandra, HDFS, whatever, do a query, and then give you the result. Druid is more something where data lives. So Druid has its own storage format. Presto doesn't really have a storage format. It pulls data from wherever it is and whatever format it's in. In Druid, you can only query data that's actually in Druid's format. So I think that they aren't complementary now because there is no Presto Druid connector, but that's something that would totally make sense, and it's actually something that I think would be cool to build. Like something that you could actually use Presto to pull data out of Druid and then crunch it in Presto to do sort of like, so you were asking about joining two tables. That's a query that Druid doesn't support because Druid targets very fast queries. You just can't do that fast. But it would make sense to potentially pull data from two tables out of Druid into Presto and do a join there.
For recomputing data from a batch job, is there some kind of a file format or something for Hadoop?
So the question is, mechanically, how do you actually recompute data from a Hadoop job? There is a MapReduce job that comes with Druid that you configure it with where your data is in HDFS, and you run the MapReduce job, and it spits out the Druid segments.
So what does imply?
Last question.
What does imply provide? Like, is it a services company, or is there a platform that goes along with it?
It's a great last question. I did not even ask him to ask that. So yeah, we're a services company. So we're doing support for Druid. So if you're running Druid on premise, then we help you out with that. Thanks everybody.
Stick around, ask more questions after. Everybody.
I didn't know how much provided.
Like individual
No, there's actually no security support at all. So most people that have security needs like that front it with some kind of proxy. They have a proxy that looks at queries coming in, decides if they're okay.